This section is going to look at one way that we can apply sine and cosine, and that is in harmonic motion. So, simple harmonic motion. An object that moves on a coordinate axis is in simple harmonic motion if its distance from the origin at any time is given by either d equals a cosine omega t or d equals a sine omega t. So d is the distance, t is our time. What's a and omega? And yeah, the omega is the W looking thing, by the way. So the motion has amplitude A, and that is the maximum displacement of the object from its rest position. And then the period, just like normally when we had a cosine of bx, this time it's a cosine of omega t, same deal. So the period is 2 pi over omega instead of 2 pi over b, but same idea. In describing simple harmonic motion, the equation with the cosine is used if the object is at its greatest distance from rest position. By contrast, you use sine if the object is at rest position at the origin. So that tells you whether you use sine or cosine. Example 1 says a ball on a spring is pulled 6 inches below its rest position and then released. The period for the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. So the ball is released at t equals 0, where the ball's distance or maximum displacement is 6 inches. So that means, since we're starting with it pulled down 6 inches, that means we're using cosine. The other thing that means is that our amplitude, since it's being pulled down 6 inches, A will be -6. Of course, the amplitude is 6, but A is -6 because it's being pulled down. So far we've got A, we just need omega. We're told that the period is 4. So we can find omega by plugging in 2 pi over omega for the period. So omega would be pi over 2. Now we can write our equation. D equals -6 cosine of pi over 2t. The frequency of an object in simple harmonic motion is given by omega over 2 pi. That might look familiar. That's the period. The frequency is 1 over the period. Okay? So it's just flipped. Example 2 says an object moves in simple harmonic motion described by D equals 12 times cosine of pi over 4t, where t is measured in seconds and d in centimeters. Find the maximum displacement, the period, and the frequency. So, the maximum displacement is just A. So the maximum displacement is 12 centimeters. The period is 2 pi over omega. So that's 2 pi over pi over 4. Flip and multiply. And we just get 8. The frequency is 8. Or the period is 8. And then the frequency is 1 over the period. So it is 1 over 8. Example 3, an object moves in simple harmonic motion described by d equals sine of pi t minus pi over 4, where t is measured in seconds and d is in inches, and we want to find the maximum displacement, period, and frequency again. So, same type deal. The maximum displacement is the number in the front, which in this case is just 1. The period is 2 pi over omega, that's pi, so 2. And the frequency is 1 over the period, or 1/2. Example 4, a block hangs on a spring attached to the ceiling and is pulled down 8 inches below its equilibrium position. After release, the block makes one complete up and down cycle in 5 seconds and follows simple harmonic motion. What is the period of the motion? Well, the period is how long it takes us to complete one up and down cycle. So the period is 5 seconds. Part B asks, what is the frequency? Well, the frequency is 1 over the period. So it's 1 over 5. Or if we want to write that as a decimal, 0.02. And last it asks, what is the amplitude? It says that it is pulled down 8 inches. So the amplitude would be the absolute value of A, which in this case is it's being pulled down 8. So the amplitude is 8. While A, which we'll need, is negative 8. So D says write a function to model the displacement in inches as a function of time. Okay, so we've got all the information that we need here. Since it's being pulled down 8 inches to start, then we're using cosine. And we were given that, or we found that the amplitude was 8, or A is negative 8, since it's being pulled down. And we found that the period was 5. So we need to find omega. So 2 pi over omega equals 5. 5 omega equals 2 pi, so omega is 2 pi over 5. T. So that's how you write a formula for simple harmonic motion given a situation. We're going to look at one more example of a situation here. It says a Ferris wheel is 120 feet in diameter with its lowest point 2 feet off the ground. The wheel makes one full rotation counterclockwise in 2 minutes. Suppose that someone is seated at the lowest point on the wheel and is the last passenger to be loaded when the wheel starts. Write a model representing the last passenger's horizontal position, x in feet, relative to the center of the Ferris wheel, t minutes after the ride starts. So, first of all, we're going to need A. And we're thinking about this relative to the center. So we need the distance for this person from them to the center of the Ferris wheel. It says the Ferris wheel is 120 feet in diameter, so the distance from this person to the center must be half of that, 60 feet. So that means that A must be 60. Then the period, we were told, is 2 minutes. So we can find omega. Omega will be pi. So let's see. We need to know last, are we using sine or cosine here? Well, it says that we're starting this with the person seated at the bottom of the Ferris wheel, okay, in the initial position. So the initial position is at 0. So that means that we're going to use sine. So we plug in A. We have sine of omega t. Then for part B, we're going to look at it a little bit differently. For part B, it says, write a model representing the last passenger's height, y, in feet above the ground level, t minutes after the ride starts. So we want to think about how this person is the last person, because that would be when it actually starts going around, because if you've ever been on a Ferris wheel, you have to wait till everybody gets on, right? So we want to think about when this person is going to be at the bottom and where they're going to be at the top. If we draw a little graph here, then, I don't like that line. There we go. Then we know it said back at the beginning that the Ferris wheel was 2 feet off the ground. And that makes sense because it wouldn't be able to touch the ground and go around, right? So it's going to mark here at 2 feet. And then it says that it's got a diameter of 120, and half of 120 is 60. So that would be our radius, half the diameter. So think about along some midline here. The Ferris wheel is going to start down at 2, and then it's going to go up or around that last person, and then it's going to come back. That last person is going to come back to the ground. And it'll keep going, but right now we're just looking at 1 revolution. So where would that midline be? Well, while he's at the bottom, when he gets halfway up, then he's gone half the diameter or the radius. So this distance here would be 60. So if that distance is 60 and we add 2 to that, then that means that this spot here on the y-axis is 62. So the vertical shift is starting at 2 and then adding the radius of 60. So it's 62 feet up for our midline. To find the period, we know that the period is 2 minutes. So the period is 2. To find omega, that is 2 pi divided by the period, or pi. And lastly, what's the amplitude? So the amplitude would be the distance from here to here, or from here to there, right? So the distance, the amplitude, would be 62 minus 2, or 60 feet. So if we plug into our formula, we've got D equals A cosine of omega t plus our vertical shift. Then we've got the amplitude we said was 60. But normally cosine starts up here and goes down. So since we're starting down and going up, then it's going to be negative. Then cosine of omega, which is pi, times t plus our vertical shift, which we found to be 62. So there's our equation. And that concludes this part of simple harmonic motion.